And we're back with lesson 1.1.4. What if I move a non-parent graph? They're calling them arbitrary graphs. So basically, that's something that falls outside the realm of our x squared or x cubed or 1 over x or 2 to the x, so forth. How do we sketch transformations of parent graphs and non-parent graphs is our lesson essential question. And we're going to start here. Problem number 43 just talks a little bit about familiarity with the calculator. That's something that we can answer in class if you have questions. Obviously, I'll be using the calculator during the course of this lesson, and if you can follow along with your calculator at home, that'd be great. Number 44, the graph of f of x equals x cubed minus 3x squared plus 5 is shown at the right. Enter f of x into y1 of your calculator. So I'm going to go to my calculator. The on button always helps. I'm going to go to y equals. I'm going to type in this particular equation, which is x cubed, all right, minus 3x squared plus 5. I can go ahead and hit graph, and it'll give me the same graph that the book is giving me. Okay. Now, enter for y2. Enter y1 of x minus 3 plus 2. So go back to y equals. Hopefully you remember how to find the y1. Vars, y vars, function y1. And we're going to go with, it's giving us x minus 3 plus 2. Now, you recall graphing transformations. Predict what's going to happen. Well, we have a minus 3 inside parentheses. Remember, again, inside parentheses means two things. It means opposite and horizontal. So that's going to be a right 3. And we have plus 2 outside, so that's going to be an up 2. So this whole graph should get shifted to the right 3 and up 2. All right, so if I move each point right 3, okay. I should be able to get my new equation or my new graph, which should look something like this. Okay, and then up 2 would be the second shift. So I'd have to take each of those points and move them up 2. If you're somebody who can do all of this in one step, fine. Do all of it in one step. All right. Okay. So that's going to be a general sense of what that final graph looks like there in red. We can use our calculator to get that. So here's y2. Scroll all the way over to the left and hit enter once. And you'll notice how that line becomes a little more bold. So what's going to happen here is it's going to give us our original equation, and then our shifted graph is going to be in bold. So here it comes. There we go. Is it what we thought? Right 3 and up 2? I would say so. So how would you modify f of x so that the graph shifts 4 units to the left and down 2? So go back to your y equals. We want 4 to the left, so that's inside, plus 4, opposite. And we want it to go down 2. So let's change this to a minus. Don't change anything else. Go ahead and hit graph. Our original graph comes up first. Our shifted graph of left 4 and down 2 comes up second. And I would say that's pretty good. Now modify your equation in y2 by entering y2 equals negative y1 of x. Predict what will happen. Well, we said before that that negative symbol, that negative a value, is going to reflect the graph about the x-axis. So let's insert that negative value there, and we can delete the rest of these pieces. So what should happen here is if I take my original graph, each of these points should be reflected across the x-axis. So these points will end up looking like this, and the x-intercept will stay the same. Okay, so my graph here will look like this. And you see how that's a reflection across the x-axis. So hopefully my calculator verifies that. Original graph is going to appear first. Reflected graph is going to appear second. Okay. Now it does ask us what point doesn't change. Where is that point? Why did it not change? So hopefully you can recognize the point that doesn't change is the x-intercept. Why didn't it change? Well, because a 0 times a negative is still 0. So zeros are never going to change anytime you're doing this. Add a sketch of the function by entering y2 is 2 times y1. So now instead of reflecting it, we're going to stretch it vertically. Okay, so that 2 is outside, which means vertical. All right, and it's a stretch. So here we go. Graph the original, stretch the new one, which means my maximum value there should get stretched. Good. All right. So you can see here how it looks as though we just took this point here and pulled it up to get the new one. That point there was also pulled up a little bit. They were actually each doubled. All right, again, what point doesn't change? It's still the x-intercepts that doesn't change. Okay, it's zeros, because 0 times anything is still 0. The graph of g of x is shown at the right. It's a transformation of f of x. Express g of x in terms of f of x. So if I go back here to my f of x, I look at some of the important points that I have here, which would be 0, 5, and 2, 1. And then go to my g of x, plot those points, 0, 5, 2, 1. And then try to figure out how they got shifted. So this point here looks like it got shifted to the left 2 and down 1. Does this one match? Left 2, down 1? Yes, it does. So I'm looking for an equation that goes left 2, down 1. So I'm going to do g of x equals f of x. Left 2 will be plus 2, inside and opposite, and down 1 would be minus 1. Suppose that we have a stretch with a shift, okay? So which one's going to come first? That's an order of operations deal, okay? So we're going to refer to, please excuse my dear Aunt Sally for that. And what comes first, multiplication or subtraction? Well, multiplication comes first, subtraction comes second. So you always stretch your graph before you shift it, okay? Now here in part B, they modified that, they used parentheses. Well, obviously parentheses trumps everything. So here, the down 3 will happen first, and then the stretch of 2. And you can use your calculator to verify that, but order of operations is what we're going to talk about, what we're going to use. Okay, so resource page that you should already have. All right, and go ahead and we're going to do some of these together, not all of them. But if this is f of x, we want to graph f of x minus 2. So what I'm going to do here is look for important points, such as zeros and vertices. Okay, so I'm going to use those points, and I'm going to move all of them inside parentheses and opposite. I'm going to move them right to. So this point here is going to come right to. This point is going to go right to. This point right to, and right to. And then I can sketch my graph, and I'm done, just like that. Now I'm getting a negative 2 times g of x, so I'm going to take my important points, vertices and zeros if I have any, and I'm going to multiply them by negative 2. So 2 times negative 2 is negative 4. 0 times negative 2 is 0. Negative 1 times negative 2 becomes positive 2. And then negative 3 times negative 2 becomes positive 6. And there's my new graph. Stretched by 2 and reflected. Now I have a combination here. I have a right 1 and I have an up 3. I don't care if you do them one at a time or if you do them simultaneous. That's entirely up to you. Again, choose some of those important points. Here, here. I say zeros, but that's a whole number of values. So that's going to work a little better. Okay? And each of those are going to go right 1, up 3. So this point here is going to go right 1, up 3. The y-intercept is going to go right 1, up 3. This point is going to go right 1, up 3. And then last I have this point going right 1, up 3. So I have a two-part problem here. It's a parabola combined with a linear. That's called a piecewise function. We'll learn more about that in Unit 2. Now, here are the stretches with the vertical shifts, the ones that we were talking about. Order of operations applies. So the stretch happens first and then the vertical shift. They give you two graphs here in case you need to do it one step at a time. It's up to you. Again, important points. And you're going to times those points by 3 and then bump them up 1. I'll do the first one here in 2 steps. So first, 0 times 3 is 0. Let's see here, we have 2 times 3 is 6. And we have negative 2 times 3 is negative 6. And then we have, oops, that was 5. There's negative 6. And then we have 0 times 3 is 0. So There's my stretch. Okay, and then I take each of those points and I bump them up one more from where they are. So up one, up one, up one, and up one. And I draw my graph. Now you should be using a ruler, I'm not. I do have a straight line function for this, but I'm not going to do it. So there you go. Next, times by -2 and then right one. So parentheses should happen first here. So we're going to do the right one first. Again, I'll do step by step. So this will be a right one, and this will be reflect and stretch 2. So right one, again, important points. All goes back to those. Move each of them to the right one. So that point goes right one. This point goes right one. This point goes right one. And this point goes right one. And then you can sketch your graph. So I took care of the horizontal shift. Now I'm going to take each of those points and I'm going to times them by -2. So 0 times -2 is 0. 2 times -2 is -4. Okay, we have -2 times -2 is +4. And last we have 0 times -2 is 0. So you see that that flips my graph and stretched it by 2. So it's been stretched and flipped. Last one, 1/2, and then +3. So again, I'm going to do the half first. So important points. I'm going to do this all at once. So follow along. 0 times a half is 0 plus 3. 1, 2, 3. 2 times a half is 1 plus 3. -2 times a half is -1 plus 3. And finally, 0 times a half is 0 plus 3. So you see how my graph has been shifted up and it looks like it's compressed. Oh, sorry, one more. Didn't know that. So now we have a right 2 and a 1/2. Why don't you go ahead and try that one on your own? And there should be your answer, right 2 and 1/2. So verify that. If it's not correct, then feel free to ask questions. All right, here again an idea for Unit 2. Remember this, the idea of transformations can be applied to other graphical representations such as area. The graph below at the left shows the area under the graph of f of x between 0 and 2. So between 0 and 2, this is the area under the parabola. Okay. How do the areas of the shaded regions f of x and f of x minus 2 compare? They're the same. All we did was take this section here and shift it. Okay, it went from here to here. The area did not change. So areas are equal. That is a key idea of Chapter 2. And if you learn that now and tattoo that in your brain, you'll be good. The original interval for the shaded region was 0 to 2. Over what interval is the shaded region here? Well, here it's 2 to 4. Which should make sense. Okay, why should that make sense? Well, we moved our whole graph to the right 2, which means we're going to move all of these points to the right 2. So 0 plus 2 is 2, 2 plus 2 is 4. When we shift the graph of f of x to the right, we replace the x with x minus 2 in the function. Can we use a similar technique to find the shifted interval in part b above, which is what we just did. Suppose the function is f of x plus 3. That means it's going to go left 3. Okay, so instead of going to the right 2, all right, here it is, we're going to go left 3. 1, 2, 3. Did the area change? No change in area. No change in area. Horizontal shifts do not change area. Okay, however, our interval does change. Our interval here is now going to be -3 to -1. And again, you just look at the shift and what's been done there.